So chapter 4, if you remember, we have discussed the second law of thermodynamics. And again, we said this law complementing the first law of thermodynamics. First law of thermodynamics is just related to the energy and how the energy is changing its form from one form to another one. But we need more information about this process will occur or not, but about the efficiency of the process. So this is where we have the second law of thermodynamics. We introduced the entropy, and we said how entropy is related to the work loss. Entropy is related to the process will occur or not. And we explained some examples of thermal efficiency. The last thing we explained in previous lecture are different ways we can use to calculate the efficiency. And we said we have, so far we have discussed three types of efficiency. We have discussed general thermal efficiency, so the first one. And last lecture we talked about two other types of efficiency. We can call them isentropic efficiency. General thermal efficiency, we saw this equation when we talk about the heat engine. So we said we have work producing device similar to the heat engine. For this work, we have input heat and we have the desired output is work. So the efficiency of the heat engine is whatever useful product we have, whatever the desired output you will need to obtain from this device, divided by the input. So this one will be the net work, the amount of work that we obtain from this device, divided by the amount of heat you are adding to the working fluid at the hot temperature reservoir. Or it can be rewritten as 1 minus Q released at the low temperature reservoir divided by Q added at the high temperature reservoir. So any of these forms of the equation you can use to calculate what is called the thermal efficiency of heat engine. But then we said we have other work producing devices or work consuming devices. An example for this one is turbine. An example for this one is pump or compressor. So we have efficiency for this piece of equipment, and this efficiency called isentropic efficiency. So for turbine, we said the efficiency for this turbine is the actual amount of work we are obtaining from this turbine, if this turbine operates in an irreversible way, divided by the maximum or theoretical amount of work that theoretically you can obtain from this turbine if it operates in a reversible way. So this is called isentropic efficiency because here we are dividing by the maximum or theoretical efficiency if the process is reversible. And the process is reversible if the entropy is constant. And the entropy is constant, or the change of the entropy is zero if the process is isentropic. So this isentropic means we don't have any change happening in the entropy, or we have the generation of the entropy. This is called zero. And this condition, this is the condition that will give you the maximum or theoretical work output. So this is called isentropic efficiency of turbine. The actual amount of work you are obtained from this turbine divided by the theoretical or maximum amount of work that you may obtain from this turbine if there is a possibility that this turbine operates in a reversible way. Same thing for work-consuming devices. So we said the isentropic efficiency of work-consuming devices, pumps, compressors, fans. This is the minimum or theoretical work input divided by the actual work input. Minimum or theoretical work input, this is the amount of work that you give to this device in order to operate. And this amount of work is minimum if the process is ideal, if the process is reversible. So this is why here we have reversible a process. This gives you the minimum input as well. Actual work input, this is for irreversible process. So just be clear, sometimes you have isentropic efficiency, it's work irreversible divided by work reversible. Sometimes it's work reversible divided by work irreversible. So you can have different equations for the same thing, but the difference here is what is this device? This device is producing work, or this device uses work as an input. So if this device produces work, So the efficiency of this device is work irreversible divided by work reversible. If this device needs work as an input, so the efficiency is work reversible divided by work irreversible. So let's see this picture. So this is the picture of the heat engine we have. So as we said, if you are studying the whole heat engine, then you can calculate the thermal efficiency of this heat engine. For this heat engine, we have Qin. This is the amount of heat we are adding to the working fluid, and we have work out we are obtaining from the turbine. We have work in we are adding to the pump, so we can calculate thermal efficiency of the whole heat engine, and this will be the equation we have. So this equation calculates thermal efficiency of the heat engine. So it calculates work in or net work obtained, which is work in minus work out, divided by Qin, or 1 minus Q out, the amount of heat released here, divided by the amount of heat input. So this equation, I focus on the whole heat engine, not the turbine, not the pump, not the boiler, not the condenser, but all of them together. So all the 4 components of the heat engine together, we can calculate for all of them. So what is we define as the thermal efficiency. But you can study this turbine, only the turbine. So this turbine is work producing device because we have work is obtained from this turbine. So now if you are studying this turbine, you can define the efficiency only for this turbine, and this is what is called the isentropic efficiency. So the isentropic efficiency is just for one component of the heat engine. Similar, we can have the pump. You can study this pump, and you can define the efficiency for this pump, and this will be the isentropic efficiency. So this is isentropic efficiency. Of pump, and this equation here, this one is isentropic efficiency of turbine, but this one here, this is thermal efficiency of the heat engine. And the heat engine consists of 4 components: turbine, the pump, the condenser, the boiler, all of them at the same time. Clear? So when you read the problem or when you see the given information of the required, just make sure that you have thermal efficiencies given for the whole heat engine, or you have efficiency of turbine given, or efficiency of pump given, because we can express efficiency in different ways. Sometimes we can express efficiency only for single components or for the whole heat engine we have. Clear? Any questions? Okay. So this is why if we have like, we're going to check this isentropic efficiency. So let's say if you have turbine, for example, and this turbine produced 800 kilojoule per kilogram. Okay. So now if you can see this number represents the actual amount of work we are obtaining from this turbine, or the theoretical one. This is the actual one. He says we are producing this amount of work from the turbine. So we have, this is the actual. But the reversible or the isentropic, this is why it's called isentropic efficiency, the reversible expansion could yield 1,000 kilojoule per kilogram. So this is the maximum amount of work or theoretical amount of work we can obtain from the same turbine if this turbine operates in a reversible way. So if you need to calculate the efficiency of the turbine, so this will be the actual amount of work you are obtaining divided by the theoretical amount of work we are obtaining, so it will be 0.8 or 80% efficiency. This is not thermal efficiency, this is isentropic efficiency for this turbine. Clear? Any questions? We have the same thing we can have for pump or for compressor, for example. So we have here compressor. This compressor requires 250 kilojoule per kilogram as an actual work. So this compressor to work, to function or to operate, it needs this amount of work, 250. While the reversible or isentropic compression would require 200. So if the process is ideal without friction, In a reversible way, in isentropic way, only 200 kilojoule per kilogram will be enough. But as we said, reversible process does not exist in real life because we have friction, we have losses happen. So if you give it 200, it will not like function in the proper way that you need. So you will need to give it extra work. So the actual amount of work you are adding to it is 250. Okay. So if you need to calculate the isentropic efficiency for this compressor, so this would be the actual amount, sorry, the theoretical amount like this compressor needs, or the minimum amount this compressor needs, divided by the actual amount this compressor needs. So you see difference. Oops. So here we have actual divided by theoretical or maximum. But here we have minimum or theoretical divided by actual. Is it clear?